Disappearing coin trick. Place a coin in the bottom of a beaker, push the beaker away until you just can't see the coin anymore. Now, slowly pour water into the beaker and watch carefully. As if by magic, the coin appears. Here we can see a ray of light being refracted as it passes through a glass block. The diagram shows clearly what happens to the direction of the ray of light as it goes through the glass block. Let's look more closely at what happens when a ray of light moves from air into glass. So here we've got the boundary between the air and the glass, and I'm going to draw my ray of light. There's my instant ray, and whenever we're dealing with light we need to construct a normal, which is a construction line at 90 degrees to the surface, and we see that when the light goes into the glass it bends, it changes direction like that, so the angle outside is bigger than the angle inside, and we say that the light bends towards the normal. What causes the ray of light to change direction when it enters the glass? Well, let's look more closely at this beam of light coming in here, and we'll think about the wavefront that's just touching the glass at this end. So in the air this wavefront is going to travel from here to here, but in the glass the light travels more slowly, so it doesn't travel as far, so it's only going to travel to here. So I get a new wavefront, which is there, and the light is travelling at right angles to that, so I can draw in the new direction, which is there. And that change in direction happens because the light slows down as it enters the glass. So if I draw in some more wavefronts to represent the wavelength there inside the glass, the wavelength is shorter because the light is travelling more slowly. Here we can see a ray of light being refracted as it crosses the boundary between air and glass. It was a Dutch mathematician and astronomer who first found a rule that links the two angles marked here. This one we'll call the angle of incidence I, and this one the angle of refraction R. And Snell found that the sine of angle I divided by the sine of angle R was equal to a constant n that he called the refractive index. Now this change in angle, change in direction, is caused because the light is slowing down as it goes into the glass. So the refractive index actually depends upon the change in the speed. So I've got here some values for the speed of light. In a vacuum, 3 times 10 to the power 8 meters per second. In air, it's just about the same. In glass, it's 2 times 10 to the 8 meters per second. In water, 2.26 times 10 to the 8, and in diamond, 1.25 times 10 to the 8 meters per second. And it turns out the refractive index is equal to the speed of light in a vacuum divided by the speed of light in the material that the light is going into. In this case, it's glass, so Cg. So using the values that we know, so Cv is 3.00 times 10 to the 8 meters per second divided by glass, which is 2.00 times 10 to the 8. So N for glass, the refractive index for glass, must equal 3 over 2, which equals 1.5. There are no units because we divided a speed by a speed. For a transparent material, I can define what we can call the absolute refractive index. So here for material 1, I can talk about N1, the absolute refractive index, being equal to Cv, the speed of light in a vacuum, divided by C1, which is the speed of light in the material. I can do the same for material 2. So the absolute refractive index for material 2, N2, will equal the speed of light in a vacuum divided by the speed of light in material 2. Now let's think about what happens when light passes from material 1 into material 2. So we're not dealing with the vacuum anymore, the light's going straight from material 1 to material 2. So let's call that angle theta 1 and that angle theta 2. And so I can say that the refractive index N from material 1 to material 2 must equal, using Snell's law, sine theta 1 over sine theta 2. And that must equal the speed of light in material 1, so that the speed of light is C1 there, and the speed of light is C2 there, so that must be C1 over C2. So how does this refractive index here for these two materials relate to the absolute refractive index for the two materials? Well, I can say that the refractive index N from 1 to 2 equals C1 over C2, which equals C1 over CV times CV over C2. So looking at what I've got over here, CV over C1 is 1 over N1, so N from 1 to 2 equals, well, that's 1 over N1 times CV over C2 is N2. N2, so the refractive index from 1 to 2 is equal to the absolute refractive index N2 divided by the absolute refractive index N1. So the refractive index for a ray of light passing across the boundary between material 1 and material 2 is n from 1 to 2 equals n2 over n1. Now light has a property called reversibility, which means if I shine a ray of light in this direction here, it will retrace its steps and come out there. So with a little bit of algebra you can show that n from 2 to 1, so going from this material to this material, must equal n1 over n2, so that equals 1 over n from 1 to 2. Using Snell's law again, we can generate another useful equation, because we had previously that sine of theta 1 over the sine of theta 2 was equal to n2 over n1. So it's this refractive index here. And I can just rearrange that to simplify it. So I get n1, the absolute refractive index of material 1, times sine of theta 1 is equal to n2, the absolute refractive index of material 2, times sine theta 2.